Okay, welcome back for day 2 of our summer school on fire safety science while on fire behavior. So I may have some couple of comments to make along the during the day, but let's get started right here. Please make space for people who may be latecomers, and this morning we have talks that are going to look at, again, some physical aspects of flame spread and combustion. So the first talk will be presented by Sarah McAllister, Dr. Sarah McAllister from the Missoula Fire Sciences Laboratory. And Sarah is going to talk about flame spread and also a little bit about ignition. Sarah, the floor is yours.
Only because Arno forced it on me today. But it's great, though. I actually really like ignition, so I could talk all morning about it. So
Turn on the...
I think I'm on. Yeah. I'm on, but do I need to move it up a little? Well, this thing is, women's clothes don't really make for convenient places to put things. So I actually wanted to start today by just a quick poll of people, because this is the Combustion Institute Summer School on Fire Safety Science on Wildland Fire. So I kind of have possibly 3 communities here. Who would identify as combustion? Okay, we got a couple. Who would identify as fire protection engineering? Okay. How many people identify as wildland fire? Okay, so there's some good overlap here. Okay. So I will try to cover all of it in my talk, which is really hard, right? With a topic like flame spread, it's in all 3 aspects, and I'll do my best to at least kind of go through it. But first, I'm going to derail myself immediately and talk about fire ecology. This is a topic that I think is really important, not only as just citizens of places where fires happen, but also as students of wildland fire. Because it's really easy to get stuck in the bad things about fire, right, and forget about all of the good things that fire can do for ecosystems. I'm a Forest Service employee, and it's really easy to forget that the Forest Service is not a fire service. We don't exist to strictly put out fires, right? We are supposed to be sustaining the health and diversity and productivity of the nation's forests and grasslands, right? We're not solely to put out fires. And don't get me wrong, there's plenty of bad things about fire, right? I mean, Alex showed plenty of really bad examples of bad fire in Australia. There's plenty of bad ones, good bad examples in the U.S. I just put up one here. It was the Marshall Fire in Boulder, Colorado, which was essentially New Year's Day. Over 1,000 structures, almost 1,100 structures lost in a 6,000-acre fire. And you can see it was really a very wind-driven fire. It was dry for New Year's in Colorado. There was no snow, and it just tore through a community. Bad fire also, is talking about structure loss, right? So this is just going back to about 2010, which is where I can easily find some statistics. And our bad fire years are where we burn over 25,000 structures in a year, right? Like that's bad fire. When we lose communities, when we're choked with smoke, that's bad fire. And it's not just a localized smoke effect, right? If you were in the U.S. anywhere, pretty much in 2020, you would have smelled smoke from California, right? It carried all the way across the country. And when people talk about fire and how bad it is, they often will throw up some statistics like this. A lot of times I'll talk, really only about the last 10, 20 years, but, they'll show a graph that looks something like this, where you've got area burned in hectares, that's the blue line, and then the number of fires in orange. And, they'll talk about how, especially looking at since about 1995, there looks like this really apparent increasing trend in the number of acres burned, where the number of fires has stayed relatively constant. But I want to take a step back and put this graph into perspective, at least for the U.S. And I will admit my perspective is pretty Forest Service centric, but I think a lot of Forest Service policies has really bled over into a lot of other agencies and how we manage our land and how we think about fire. So the Forest Service was born in 1905, as it's in the way it currently is, and we manage 193 million acres, which actually isn't the largest land management agency in the U.S., but it's still a pretty good chunk, right? And little possibly unknown fact is that the Forest Service is actually part of the Department of Agriculture, not the Department of Interior like the national parks and everything. And that's because we also do timber management. And that was really important back in the early 1900s. So we have this fledgling agency that is here to manage timber and do all the really great industrial things that built America. And then 5 years later, we had a set of fires that burned 3 million acres in 2 days. The 1910 fires in northern Idaho and western Montana. So you go back to those statistics on how many million acres in a bad year is 10 million acres. We burned 3 million in 2 days in that year, right? So you can imagine that shocked us, and it was really scary. So after that, we really started to fight fires very aggressively. And by 1935, we had the 10 a.m. policy officially in place, which meant that any fire had to be extinguished by 10 a.m. the next day. And if it didn't work, then you were on for the 10 a.m. the next day. So it was just aggressively getting after every little fire start that happened. In 1944, we got Smokey Bear, which is possibly the most effective public ad campaign ever. Because if you've ever lived in this country, you know only you can prevent forest fires, right? Everybody knows that. He's a very familiar face. He's on every Forest Service land pointing to what the fire hazard is every day. So everybody knows it, right? And we have this fire bad mentality. So follow this by the 1950s and 60s where we had relatively mild summers, right? Didn't have a lot of fires. So that helps put that, first part of that graph, that right side or the left side, in perspective, right? Because we just didn't have fires. We were fighting them. Nothing went anywhere. And then all of a sudden now we're like, oh my God, we have fire. But if we go back in that graph a little further in time, back prior to the 1950s, we'll start seeing some really interesting things. So back in the 1930s, for example, we were burning about 20 million hectares a year, right? Bad years now are 4 million. If we go back even further, oops, wrong way, you'll see that back in the 1700s and even before, we were burning 80 million hectares of land in the U.S. every year. That's a lot, right? And we know this, and a lot of this was because of the Native Americans, right? They were here, they were using fire as a tool, and they were very active land managers. They used fire for all sorts of things, from clearing land to just navigating, to hunting, to producing acorns for food, to producing shoots for their baskets. It was a really useful tool, and they used it all over the place and quite frequently. The other reason is because lightning, right? Lightning has always been a thing, is a thing, and will always be a thing. So this graph shows the areas where lightning is more of a thing. So the blue is more where lightning is the predominant cause, where the redder colors are where human-caused ignitions. But you can see all over the West Coast, primarily, is very heavily dominated by lightning-caused fires, right? So these have always been around, will always be around. So fire, has always started. So if we then take that graph of our scary acres burned and put it on the same units, the same axis as historical, what we burn now is barely a blip, right? So you might be wondering, how do we know any of this? How do we know how many acres burned in the 1700s? And that is because we have fire ecology. So fire ecologists, among other things that they do, study past fire behavior, fire regimes, they call them, where fire happened on the landscape, how frequently, what kind of fire it was. And one of the things they do is they go through these forests and look for these fire scars on these trees. So an area where a tree kind of partially burned. And these form where there's a low-intensity fire. So sometimes a low-intensity fire will come and hit these trees and absolutely nothing will happen. They have really thick bark, and they come out of it completely unscathed. But other times it might be a little intense, or there's a little pile of duff or needles or something at the base of it, and it'll wound the tree a little bit on the outside. And so now the tree is open. And so you'll have these fire scars, and they're called cookies when they cut them. One tree that does this really well is the ponderosa pine. And I'm going to use this as an example because it grows all over the West Coast, all over California, Washington, Oregon, Montana, Idaho. This is a really common tree to find. Probably find some random ones around campus just because they kind of grow everywhere. So if you look at one of these fire scars, one of these cookies, you'll see something that looks like this. So they'll cut a little section out of the tree. It doesn't kill it. but you can start piecing back the fire history in that area based on where the scars are relative to the tree ring, right? So once it's open, it's really susceptible to further injury, and it was a really good record of the fires after that. So this tree obviously sprouted like really early, really long time ago, because there's quite a bit of tree that grew before it finally was opened up in 1659. But from there, a fire hit this tree about every 10 years until 1915, when no more fires were recorded, right? So this is just one tree example. So if you do this over a bunch of different areas and sample a lot of different trees, you can kind of start piecing together more of a regional fire picture. So this is one study that was done in Arizona and New Mexico, because not every tree records every fire, right? And sometimes fires happen over large areas, sometimes they're small fires, back in the day at least. So you see, on all of those little tick marks, the yellow ones are sub-regional or local fires, somewhere where maybe only a couple trees recorded a fire. But the red ticks are where a lot of trees recorded fires, so those are considered regional fires. So even prior to all of our fire suppression and climate change and all of these things, there were still regional fires that happened. But they were still in relatively low enough severity to not kill the tree, right? That's kind of one of the big differences. But so you see, at the record, it kind of stops after 1900, right? So we've had very little fire after 1900 when the Forest Service became a thing, and that has had a really drastic impact on the way these ponderosa pine forests in particular look. So this is a series of pictures that were taken in the same spot over 80 years. So you see the first one in 1909. You have just a few sparse trees. They're very big. A famous conservationist, John Muir, would call this open and park-like. That's the way he described California, right? You could easily walk through these forests, ride a horse through them. But over time, because we haven't had fire in these ecosystems, they have really filled in, overgrown. You get a lot more fir trees, for example, that have grown in the shade of these big pine trees. And now you have a mess. And this is what our forests look like now, right? So it doesn't take a rocket scientist to figure out that a fire in a forest in 1989, that forest is going to be very different than the fire in 1909, even for the same conditions. And this isn't true. So this is true of a lot of different ecosystems. It's not just ponderosa pine. Another example is longleaf pine. So this is a tree that grows in the southeastern part of the U.S., I think like Florida, Georgia. And these ecosystems, because it's so productive there, basically become impenetrable in about 5 years. So they get fire every 2 to 3 years. And the Southeast actually has been really good at doing a lot of prescribed burning to keep it that way, because they've realized how quickly how things change. So one of the other concepts that's related to this I want to talk about is to not get hung up when we talk about fires and being disasters, that acres burned themselves are not the disaster. There's an ecologist, Crystal Colden, at UC Merced, who really eloquently has stated this and written a lot of really great articles on it. That size isn't the best way to talk about fires. And that first one I showed, the Marshall Fire, is a perfect example, right? It was only 6,000 acres. That's a pretty small fire in the scheme of things, in the U.S. especially. But it burned over 1,000 structures, right? That's bad. But that's not necessarily, the acres aren't the problem. It's the structures that are the problem. Another example is the August complex. So this is, to date at least, California's largest ever fire. It burned over 1 million acres. So just acres divided by 2.5 is hectares, just to put that in perspective. But if you look at the severity maps that they've done afterward, and this is soil burn severity, only 6% of that 1 million acres burned in high severity, right? This is like ponderosa pine type forests that like more of that low severity, which 36% of it was, 37% was moderate, 21% of it was considered unburned, very low burn severity, right? So in this whole big map of this fire perimeter, there was still 21% of it that didn't really burn. So for most of the days it burned on TV, it didn't look like those big scary pictures on TV, and then there's a lot of places where it actually did a fair amount of good. But the problem is it still burned 935 structures and killed a person. That's what we should be focusing on, not the fact that it burned 1 million acres. Just to kind of drive home this point too, is this is the lists from CAL FIRE. They have the top 20 largest fires and the top 20 most destructive fires, and it's really interesting to see the lack of overlap between these two. So, for example, the August complex I talked about was the largest fire on record, over 1 million acres, but it was 20th most destructive. Whereas the Camp Fire was by far the most destructive in California history. It burned over 18,000 structures, killed 85 people, nowhere on the list of the largest fires. Right, so large does not mean destructive, especially here. And what's interesting, I've highlighted the ones that were caused by lightning. There's a lot of the biggest fires that were actually lightning caused and not related to people, so Smokey Bear didn't affect that at all. So this is true of not just places in the U.S. There, over 80% of the world has some kind of fire adaptation and ecosystems that depend on fire. Different regimes, as fire ecologists would say. A lot of it is surface fire regimes, but you'll see there's some red that are crown fire regimes. I'll talk about that in just a minute. Almost anywhere you go, you can find an ecosystem that needs some kind of fire to be healthy at some kind of interval. So when we talk about fire and we talk about the bad things about fire, we should be talking about things like fatalities, homes burned, firefighters killed, public killed, things like that. But we can also talk about some of the good things that have happened, right? This is another slide from Crystal, but we're promoting the diversity in the forest, complexity, all these things that help make our forests and ecosystems resilient and healthy. So we can also throw some of that in and talk about that as well. So I've talked about that low severity fire regime, places that burned frequently. But there's other types, right? As we saw on that map. Kind of loosely, there's sort of 3 main regimes. I'm sure you could divide this up way more, but so there's that understory or the frequent low-intensity fire regime, like the ponderosa pine, like the longleaf pine. But there's also ecosystems that have adapted to stand replacement fire. And if you're talking about forests, this tends to be infrequent, but for anything, it's really high intensity. And there's places that really do well with a mixed regime of both, right? So mixed would look something like the picture on top here, where you get some surface fire, and it'll pop up and burn some canopy, but then knock back down to surface fire. And that creates diversity and opens up forests, so you don't have all your forests being the same age, which makes it really receptive to bark beetle attacks or any kind of disease or even impacts from drought. It kind of frees up the forest to be a little bit more flexible and resilient. And there's ways of talking about fire adaptations, and you could classify these in a lot of different ways. Here I've just sort of listed one way of doing it. Ponderosa pine, for example, would be a resistor, right? They can survive fire intact because they have that really thick bark. And there's a number of species that do that so that they can come out of a fire totally unscathed and be fine. There's some that are what would be called endurers because, they might be top killed. Something like the chaparral in California would be one of these. You can burn off the top, but then the roots are really strong, and it just resprouts the next spring, and it's perfectly healthy and just keeps going on with its merry life. There are some things that are evaders that can be killed by fire, but put down enormous seed banks that build up and are not damaged at all by the fire that goes by. So as soon as the fire comes and it clears the land, deposits a whole bunch of nutrients into the soil, and all of those seeds just suddenly sprout and regrow. Of course, there are some species that have no adaptation to fire. They're out there. And there's some that are considered to be invaders that come in post-fire. And this doesn't necessarily mean that they're non-native. The bottom picture here, all of those purple flowers are called fireweed. And that's actually my husband and my dog out on a hike in Banff National Park. So fireweed is a totally native species in North America, and it comes in after disturbance like fire. Here, I think it grew in after like an avalanche cleared the area, but as soon as it's got a disturbance, it comes in, it blooms, it's great, and it's used in a lot of different like medicinal treatments by the Native Americans. So it's got a lot of like good things about it. So I want to talk about some of the species that have this adaptation to that stand replacing fire, because it ranges all the way from grass up to forest. So this is a picture of the grass just outside of my own house in Montana, and this is what it looks like at the beginning of spring, right? There's a whole lot of dead grass. It looks like crap. It's gross. There's ticks in it. But, when you burn it, You could do it pretty easily, especially in spring. My fence survived. And about 6 weeks later, it grows back, and it's great, and it's beautiful, and there's no dead, and there's no ticks. So grass is one of these that really can do really well with fire. It comes right back, reseeds, and it can be quite healthy.
You do it. You said you did.
Yeah. Jason actually helped me that year. Yeah. So it's a matter of going and getting a burn permit, and in Montana it's pretty easy. Yes, I will not light the neighborhood on fire, and you do it on the right day. It's pretty easy. So this is grass. There's chaparral shrubs was another example that they'll take a good stand replacing fire every 20, 30 years and be happier for it. The other one I want to talk about is something that we learned with the Yellowstone fires in 1988. So this might predate a number of you in the room, but so the Yellowstone basically burnt to the ground in 1988, and it was a major disaster, and everybody freaked out. It was a huge fire, 321,000 hectares in this national park that was our treasure, and it was one of the. I think it may have been our first national park. It was Yellowstone or Yosemite. Very, very early on. It's one of our oldest parks, right? It's our crown jewel of national park almost. So we sent 9,000 firefighters, 4,000 military. We spent a boatload of money to put it out because we're like, oh my God, the park's burning down. And you go afterward, and it was just a moonscape. It just leveled the area. But you go now, and it's like totally healthy and happy, and you wouldn't have known that anything happened. Even as recently as it took 10 years afterward, like all these trees were growing back, and you're like, how does that happen? Well, it turns out that the lodgepole pine that grow there have a fire adaptation to that high-intensity stand replacing fire. And they only regenerate when they have that kind of fire. So their cones are completely sealed shut. And only do they open and release their seeds when they're heated. So I have a little video, hopefully this is playing. Yeah. So this is just a cone being heated up in a hot airstream. And you can kind of see it. It doesn't immediately pop open, but it kind of slowly opens.
That's your rig.
Yeah. So these trees need this kind of fire, the stand replacing fire, to regenerate. This kind of thing would happen every 80 to 100 years normally, and just completely wipe everything out and start over again. And it's great because these are actually pretty dense forests, and normally there'd just be a ton of competition on the floor. These trees wouldn't get light. These seeds would just, if they were to be released, wouldn't be able to grow. But you get a great big stand replacing fire. You wipe the slate clean, release your seeds, and got your nutrients from all the ash and everything, and they grow, and it's great. So.
It was the first national park, actually.
Oh, it is. Okay, good.
After 10 pages about the series, I could find the information.
Good. So yeah, first national. So you understand we were pretty stressed. There are other ecosystems like this. I have a slide in here for the New Jersey pine barrens. So Al Bear talked about this. They have done some experiments there. And the reason they're allowed to burn such high intensity fires there is because that's the kind of fire these forests need. So the pitch pine that grows there, which is also known as candlewood pine or torch pine, which should tell you something about the way they grow and how they burn, really also thrive with that high intensity crown fire. They'll resprout out of the actual trunks, and they also have those serotinous cones, so they also reseed after a high intensity fire. So one of the last things I want to talk about is why we have a fire problem in the U.S., right? Certainly, climate change is a thing, right? We have longer, hotter, drier fire seasons, and climate change itself has had an impact on things like drought, insects, and disease, right? Our droughts are worse, which stress the trees, which makes them more receptive to insect and disease attack. So there's a lot more dead trees out there right now, that as shown on the cover of that report. There's a lot of dead trees in California, less so now because they all burned, but we also have the growth of the wildland-urban interface. That's a problem, right? We have people in our wildlands starting fires, living near where the fires are, which challenges what we can and can't do with how we manage fires. And every fire that happens now has a greater impact on us. But the thing that gets overlooked a lot in the U.S. especially, but you can say this too of Australia and probably Canada and other places, is we kind of did this to ourselves by fighting fire so aggressively the last 100 years. We put out really good at putting out all of the small and the medium, mild to moderate fires. So the only ones that burn now are the really, really bad ones. So the Forest Service, boasts that we have a 97% initial attack success rate. So we put 97% of all fires out before they're more than 100 acres. So it means that the only fires that burn now are the worst case ones, right? So we don't have that historic pyrodiversity that we used to have. That's an ecology word. And we've loaded up the forest with all this fuel, which has really changed the way the fuel loads are, how the fuels are distributed, right? Instead of having tree canopies way, way, way up in the air and some surface fuels and nothing in between, now it's just chock full from surface to crown and across huge areas. And with different tree species, right? They used to be, in some areas, you used to have a lot more pine. Now we have a lot more fir. So things are very different. And that has also made the impact of drought, insects, and disease worse because our forests aren't healthy. So now when we have a drought, it kind of makes sense. If you only have so much water to go around and you have a lot more trees, each tree is going to get less, right? And it's going to be more susceptible to insects and disease. So there's really these three things combined to have our fire problem. And the only way really out of it is actually more fire, not less. So that puts us in, I call it a pickle, right? Because fires are inevitable. We're going to have fires. But they don't have to be disasters. And a lot of places need fire of the right kind. Sometimes it's going to look like this. But the problem is we don't mix well with it, right? So we have to figure out a way of living with it. And that's what I hope, to impart to you in the time I've totally derailed myself on fire spread. So I'll get off my soapbox and start talking about flame spread. So this is where I think it's going to be hard to merge all of the different fields, right? We've got combustion, fire protection engineering, wildland fire, to talk about flame spread because, as I was told to talk about flame spread is the word that combustion and fire protection engineers use. Wildland fire talks about fire spread. So there'll be times where we have different vocabularies for kind of essentially the same thing. And so I'll talk a little bit about that. But if you take, two things away from my talk. One, fire isn't always bad. Two is that flame spread is a series of ignitions. So if you understand ignition, you'll understand how flame spread happens. And so I'll go through how flame spread happens on a single fuel particle, so intra-fuel spread along continuous surfaces. This is the classic theories from combustion and fire protection engineering. And then I'll talk about interfuel spread between the fuels. That's fire spread and the wildland fire. I probably will skip over firebrands and spotting because Michael Gollner is going to give a whole lecture on that and then kind of give a brief intro into some of the fire spread modeling, but you're going to get talks on those too. So I will say I'm going to do this in a very high level, gloss over some of these details, and I'm also an experimentalist, so there is not a single differential equation in this presentation. And I'll talk about mechanisms of things and the processes of how it happens and not give equations. So let's first start with how ignition actually happens because it's a critical part of flame spread. So the ignition process itself, I'm going to nerd out on this. I'm going to talk about it in very great detail. It's really a three-step process. So the first step, and the one that takes by far the longest time, is you have to heat that solid up from its starting temperature up to a temperature where it begins to pyrolyze, which is that great talk that Stas gave on pyrolysis. So that's the first step. You have to heat it up. The heating can happen from radiation, convection, and even conduction because you have your firebrand can land on a fuel and that can be your heat source. But the point is you have to be at a high enough temperature for pyrolysis to happen so that you produce those gases. Charring also happens along the way if you've got a charring fuel. So once those gases form from pyrolysis, they have to escape out the solid and mix with air. So you're getting actually a pre-mixed fuel and air mixture that happens above the solid surface. And the third step is that you have to actually ignite that gas. So when ignition first happens, it actually happens in a pre-mixed flame mode. So wherever you have your pilot or the hotspot that starts the gas phase ignition, it starts as a pre-mixed flame and propagates back toward the solid. And if it's hot enough, will anchor down and that'll form your diffusion flame. But if it's not hot enough, your flame will just go out, right? But if you still have your heating source, it'll continue to heat and pyrolyze, and eventually you'll get that sustained ignition. And so this process holds regardless of whether or not you're talking about radiation or convection heating. So it's kind of a fundamental process to how it happens. And I actually have a really kind of cool video that I like to show the difference between flashing and sustained ignition. So this is just a solid piece of wood that's being heated in a fist apparatus, for those of you who know this. So I'm heating it from above. I have a coil wire igniter, and I'm blowing a slight breeze from the right to the left. So because of the high-speed camera, because it's filming at like 1,000 frames a second or something like that, and the light, you're not going to see the flame, but what you'll see is the gases, the pyrolysis gases, form and then disappear, and then form and then disappear. So let me play this. So this is about 30 seconds into heating already. So look at the area by the igniter. So that was the first flash. See the gases? There was a second flash. Third. There's a fourth. And that's sustained ignition because the gases just kind of disappear. If you look really closely, there's a faint flame at the igniter. So the reason it does this is because as you're heating it up and you're pyrolyzing, you don't have a ton of fuel, right? So you have this premix mixture, and as we know from our combustion background, right, a very fuel-lean mixture has a really low reaction rate and therefore a really low heat release rate. So there's not a lot of heat being generated, and so once it gets close to that solid surface, the heat losses are greater than the heat that's generated from the flame, so it goes out. But if you keep heating it, your pyrolysis rate increases because your temperature is still increasing, and you get richer and richer. And at some point, you actually have enough heat generation from that premix flame to offset the heat losses once it gets close to that solid surface to sustain ignition. That's my nerdiness. So because of the way this ignition happens, there's multiple different ways to set an ignition criteria, and probably the most accurate and physically correct is the idea of there being a critical heat release rate, right? Because your flame has to produce enough heat to offset the heat losses. It makes sense that that's like the most fundamental. And it's the most physically correct, but it's also the most difficult to put into a model, right? Because you have to have both gas and solid phase described. So one step down would then to be identify a critical mass loss rate. So if, as we know, the heat release rate is related to the equivalence ratio, which means it's related to how much fuel is there, it makes sense that a critical mass loss rate would also help you define the ignition because they're related. So this only requires the knowledge of the solid phase, but because you're skipping the whole gas phase part of it, it actually can be a variable. There's not like a fixed set critical mass loss rate for ignition in all cases for all fuels universal. It depends on your atmospheric conditions, the fuel you're using, the heating rate, things like that. So it's a little bit harder to use and a little less physically accurate than that heat release rate. But at least you only need to know the solid phase. But by far the easiest one and the one that most people throw around is the idea of there being ignition temperature, right? Because pyrolysis is Arrhenius, it's very temperature dependent. So the production of critical mass loss rate happens at a certain solid temperature. So, I mean, you can see how these are all related. But by identifying an ignition temperature, it's like the least accurate, but it's the easiest to implement. And just to put that perspective, so listed tabulated values for the ignition temperature of wood range from 296 to 497 Celsius. So it's not like a thing. It's not a set. The ignition temperature of wood is 350, period, the end, right? It depends. But these are all interrelated. So the other thing I want to talk about ignition is that there is a critical heat flux for ignition. Back to the theme of heat generated versus heat lost. If you have a whole lot of, just anyway, you'll have some heat that's lost. If you're on Earth with buoyancy, you're going to have natural convection that's going to help that heated solid that you're trying to ignite cool down. In wildland fire especially, you're going to have wind with forced convection. You'll have some radiation to a cooler environment. And there's other things, like your rate of heat loss increases as the surface temperature increases. So at some point, though, there is a minimum amount of heating you have to give a particular fuel that's shaped a certain way in a certain environment in order for it to ignite. And that's where that heating rate just balances the cooling rate right at that ignition temperature, or whatever criteria for ignition. So heating rates less than this don't result in ignition, but again, it's very dependent on environmental condition, as Arnaud pointed out, the fuel, right? So he mentioned that, a surface of wood, the critical heat flux for ignition is 10 kilowatts per meter squared, but, a dowel dangling in the air might be 30 kilowatts per meter squared, and that's because of heat losses. And I'll talk some more about that in a little bit with flame spread. But one thing that we need, the last thing we need from ignition time, from ignition, actually there's more, is we need to know how to predict ignition time if we're going to talk about flame spread, because flame spread is a series of ignition, right? So Stas had the equation for the thermally thick fuel here, but it's basically just a solid conduction model where you're solving for how long it takes the surface of a solid to heat to the ignition temperature. So you're ignoring that mixing and you're ignoring the chemistry times. There's different assumptions, right, for thermally thick fuels, which you would naturally use for something that's thermally thick, but I would also encourage you for things that are poor conductors like wood and wildland fuels, and if you've got a situation with high heating rates like wildland fire, to check it. Because as Albert pointed out, some of your physically thin fuels may not be thermally thin because high heating rates, you've got water content, and the threshold is not as obvious as you think it would be. So those are the equations we'll refer back to, but for thermally thick fuels, you've got the material properties that are there, the ignition temperature, and it's also inversely related to the square of the net heating rate. For thermally thin, you have a couple material properties and the thickness, and it's only inversely proportional to the heating rate, not squared. So one final thing about ignition, for real this time, that I want to talk about is the effect of moisture content. So we're talking about wildland fuels. These are real fuels. They're porous. They absorb moisture, and that affects the way things ignite and burn. So moisture content is buried in the material properties as well as the ignition temperature. So if you've got higher moisture content, you're going to change the thermal conductivity, density, specific heat, as well as the ignition temperature, right? Which makes sense because if you're heating up your fuel, you're vaporizing water vapor. So now you got water vapor diluting your pyrolysis gases. It's going to need more gases and total mass loss to produce your heat release rate. Therefore, it needs a higher ignition temperature. So if you were to look at ignition time trends for just say like a slab of wet wood, you would see that the ignition time is pretty linearly proportional to the moisture content. And that kind of makes sense, right? Because this moisture is basically a heat sink. However, live fuels are a different beast. So I have a series of graphs here with 10 different live fuel species where I'm looking at the same thing, ignition time versus moisture content. But here, these fuels were sampled over the course of a calendar year, so it's different snapshots in the growing year. So the moisture content varied naturally. And so you see for some things like sagebrush, you get that linear trend. But for other things like chamise, which is a California chaparral species, or this gamble oak that grows in Utah, there's no trend of the ignition time with moisture content. And if you look, for example, at manzanita and ceanothus, you might want to try to draw that trend, except for the 2 points over here. I'm going to use this pen, which were actually new leaves that had just flushed out in the spring. So they have really high moisture content, but ignited really quickly. So that kind of completely throws off whatever linear trend you would have had for those species. And finally, if you look at this last slide with Douglas fir, you get a nice linear trend, but featherbush and gallberry actually have the opposite trend of what you think. So these shrubs actually grow under that longleaf pine in the southeast, and they actually ignite faster the wetter they are, which is totally counterintuitive. And the reason why is this is physics I think we don't understand. So this is a featherbush leaf being heated in a hot air stream, and we're looking at it at 1,000 frames a second. And it doesn't just go quietly and ignite. You'll see here in just a second. That happens. And it's not just featherbush. So this is side by side of grand fir, which is a tree species that grows in Montana. I'm gonna move this one along because I don't have forever. Oh, I guess I can't fast forward this. So here we're looking at visual and IR at 1,000 frames a second, slowly moving it into this hot air stream. Don't pay attention to the temperatures because the emissivity was not set right. But it's there so you can see some of the things you can't see visually. And I'll just maybe drink my tea for a second while it heats up. So if you've ever thrown like a branch of green needles on your campfire, have you ever like heard them snap and crackle? Because it's doing this. So what's interesting is in the visual, you can see some of these explosions actually have flammable gas in them, and you'll see jets of flame coming out of it. Of course, this is like 2 seconds in real time, so. But you can start to see, I mean, yeah, we're getting a lot more flammable jets coming out of this. So wood doesn't do this, right? I mean, this is something completely different. And, you know, maybe I should have saved this for the panel on Friday and for the current challenges in wildland fire, because this is a huge challenge, right? I mean, live fuels can be over 100% moisture content and carry a crown fire just fine. But like a dead fuel, like a needle laying on the forest floor, can really only have a moisture content, max moisture content of 30%, because the way it stores water is very different. And even then, in the moisture of extinction, like a dry fuel can't carry fire with a moisture content above, I mean, what's a good number for 10, 12%, 15, 20%? So, but yet live fuels, 100% moisture content, burn like crazy. So you can see it's basically ignited by then. So
if you do this video with a dead pine needle, it doesn't do this yet, right?
Not anywhere near that extent. I think there's some like still remaining trapped moisture and some like terpenes or something that might be in there. But unless you if you oven dry it, you don't see anything.
Okay.
But if you just had a naturally dead needle that.
If you kill it.
If you kill it.
And if you just let it
yeah.
degrade,
and you still might have a little bit of remaining moisture content, but it doesn't do anything like that. So, okay, finally getting to flame spread. So again, the key of flame spread is that it's a series of ignitions, right? So in order to have a fire, something has to be ignited first. You have to have your first spark or your lightning strike. That fuel then burns, releases heat at a particular rate, and heat from that flame has to be transferred ahead of that to that unburnt fuel and in a high enough rate for it to pyrolyze and begin to ignite itself. So that flame acts as both a source of heat and a pilot for that next portion of fuel to ignite. The tricky part is how that heat is transferred depends on the context. And that's where we get into trouble with not knowing how to model wildland fire spread, is how is that heat transferred. Not only how is it transferred, but how far ahead is it transferred? And which is an important question, too, if you're trying to figure out when a fire will spread or when it won't, especially if you have discrete fuel particles, non-continuous fuel. Because if your burning fuel burns out in a faster time than it takes for the next fuel to ignite, your fire won't spread, right? So that helps us in wildland fire when we're thinking about thresholds for fire spread. So it's an important part of that. So getting to the classical theories of flame spread from the combustion field and fire protection engineering, the vocabulary they use breaks things down into two kind of broad classifications. So one is based on flow and gravity. So in flame spread, you would have, over a continuous surface, you have opposed flow flame spread. So that is a flame spreading into a wind, which is a similar process as a flame spreading downward against gravity, right? Because you have on Earth induced flow from buoyancy. The other way is concurrent flow, so a flame spreading with the wind, which is a similar process to upward flame spread. You also have classifications based on the thermal thickness, thermally thin versus thermally thin, thick versus thin. And because flame spread is a series of ignition, a really handy way of approaching the problem is to just say flame spread is the ratio of the heated length ahead of the flame to the time it takes that fuel to ignite. So it's a heated length divided by the ignition time. And so I had to go back and talk about ignition. And it's the same ignition theory that holds for even if you're just talking about a simple fuel just igniting. But the way that heat is transferred depends on the context. And the other tricky bit is knowing the heat transfer mechanism, but also how far that heat goes. And there are great reviews available on these classic theories, so I highly recommend you to go to them if you want more information. I'm kind of really glossing over some details here because we only have 45 minutes. So for opposed flow and downward spread, I've got this little cartoon here. So here we're looking at the flow coming from the left going to the right, and the flame is spreading into it, so it's going from the right to the left. And as you can see in the little cartoon, the flame is sitting right over the already burning fuel. So all of the heat's going into the already burning fuel and not so much ahead of it to preheat the fuel, unburnt fuel ahead of it. It's got a small radiation view factor because it's pushed back down against the fuel. So there's generally much slower spread rates for opposed flow flame spread than concurrent. And the way that heat is transferred depends on if you have a little bit on whether your fuel is thermally thick or thermally thin. If it's thick, you can have gas phase conduction as well as solid phase conduction that's helping transfer that heat ahead. If you have a thin fuel, the solid phase conduction is not so much because your fuel is thin. So it's mostly gas phase conduction. And one way to come up with a simple little analytical expression is to assume that heated length ahead is proportional to a boundary layer thickness, which kind of is a little bit of a la 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 in the way, but it's an approximation to get an analytical solution. Because I'm an experimentalist, I'm going to show some experimental trends. So these are some very famous graphs by a few of our PhD advisors. So here on the top you see opposed flow flame spread rates for thermally thick fuels. So looking at it, spread rates is a function of opposed flow velocities for different oxygen concentrations. And then the bottom graph shows it for thin fuels. So for thick, you see, especially at higher oxygen concentrations, there's this ascending branch. It reaches a peak heat spread rate, and then it'll begin to decrease at higher flow velocities. So you'll notice that the peak tends to shift to higher oxygen concentrations as you go up, but at lower oxygen concentrations closer to air, that peak is kind of lost because it would occur at a flow velocity that's less than that induced by buoyancy. So it's kind of impossible to impose an opposed flow velocity of, like, for example, 0.2 meters per second because you're going to get a 0.7 meters per second flow from buoyancy on it. So it kind of flattens out that curve. So the increase is because you're increasing your heat transfer rate, but the decrease is because it's essentially a Domkohler number effect for those combustion people. Your flow time, the time you have for your gases to react, is approaching the time that it actually takes for them to react. So you're almost just essentially blowing out your flame. So for the thin fuels, you don't really see that peak because there's a lot more heat losses in the thin fuel. So for opposed flow and downward flame spread, there is an actual analytical solution for this problem. And John Doris did this very elegant mathematical derivation in this paper in 1969, but you can actually get there by just using my little ratio and doing a little hand-waving approximation for the gas phase conduction over a distance and assuming fast chemistry. So these are the expressions then for opposed flow flame spread. You've got, for thermally thick fuels, the material properties of both the gas phase and the solid phase, and it's proportional to the flame for the opposed flow velocity. So because you've assumed fast chemistry, you're only talking about the ascending branch of that, of the flame spread graphs. For thermally thin fuels, you'll note that there isn't that dependence on the flow velocity, but there's still material properties of the solid as well as the thickness that's in there. If you want downward flame spread, you just replace the flow velocity with a buoyant flow, and you can do it that way. But you can see sort of the dependencies on the variables that are important here. So for concurrent flow and upward spread, you kind of have the opposite, right? So here the flow is going from the right to the left, and so is the flame spread. So now the flame is totally leaned over and covering the unburnt fuel and really heating it up very efficiently. So whether it's convection or radiation that's dominant depends on how big that flame is. If you're talking small flames that are laminar, it's likely convection. But as the flames get bigger than about 20 centimeters, or if they are turbulent, radiation becomes more important. But for thin fuels in concurrent mode, what's important is that the fuel will burn out at the back end, which will ultimately limit how big that flame gets. And so because the flame is leaning over the solid, the heated length ahead of it is going to be related to the flame length itself, which makes a much more complicated problem to solve analytically. So experimentally, we have trends that look like this. So for thick fuels, you get a very linear increase in the spread rate with the flow velocity. And it's possible that upward flame spread for thick fuels might increase indefinitely, but nobody's proven that. So that might be a fun experiment to do if you've got a really tall lab. For thin fuels, I said you get that burnout at the back end. So you might initially get a flame spread acceleration with flow velocity, but at some point the back end will start to burn out, which is going to limit your spread rate and your flame size. And so that it increases at lower flows, but at some point you're going to kind of reach a limit. And because you've got the flame leaned over, it's not a steady state problem in most cases. There really isn't an analytical solution to this, but you can kind of start looking at the dependencies again by looking at some of that ratio of heated length and ignition time, and using an expression for like the flame length, which I believe Arnaud showed yesterday with that Q star parameter. So by putting that in there, you can see, you'd be dependent on the heat flux from the flame if you happen to know that, and how far ahead of the flame that heating goes, as well as some material properties. So wildland fuels have a slightly different important problem, is that they're physically thin and they can burn on both sides. And this changes some things a little bit, right? So if you were to, say, take a match, like was shown here, and actually hold it the other way so that it's burning slightly downward towards your fingers, you would actually get a sharp increase in the downward spread rate just as you start to tilt it, because you'll get a little flow instability that happens underneath. And so you get this little bubble of gases that actually transfers heat really effectively on that thin fuel, only because it has the bottom can burn. Of course, if you keep tipping it downward, that'll eventually stabilize and things will become a little bit more normal. If you're looking at upward spread, that's what on a thin fuel burning on both sides, that's what that graph on the right shows. So you get an increase at all angles, right? Because flame spread happens at angles other than perfectly horizontal and perfectly vertical, right? We have slope. Things are angled. Thicker fuels don't have that bottom burning thing with the flame instability, so you don't get that little bump in the spread rate. So it just gradually slows down a little bit as you tilt it. And the really interesting thing about thick fuels and upward spread is shown in the graph here on the right. And this was talked a little bit about when Albert talked about fire eruptions, because this is also seen on a much smaller scale, as called the trench effect. So as you're angling your fuel upward, for small slopes, like less than 20 degrees, you'll get a little bit of an increase. But once you hit a critical slope at about 20 degrees, you get something called flame attachment, and you get really rapid spread rates that increase quite dramatically for every little bit of slope increase after that. And this was studied a lot after the King's Cross fire in 1988, which also probably predates you. But so it's a really tragic story of There was a wooden staircase in a metro station in London that some grease or something caught fire, and it just wooden escalator, and it just rapidly just whooshed up this escalator, and it killed a bunch of people. So Dougal Drysdale did a bunch of research on it afterward, and really studied this effect, and noticed that it's a lot more prominent if you block the entrainment from the sides. So think, like a canyon. So I'm gonna stop there with the classic theories. Kind of breeze through a lot of it because we're here for wildland fire, and spread between fuels is much more important in wildland fire. But we're also transitioning to a different body of literature, so we have different vocabulary, because now we're talking about fire spread, not flame spread. And instead of opposed flow flame spread, we have backing fire. And instead of concurrent flame spread, we have heading fire. And the other thing that you see a lot in wildland fire is flanking fire. So that's the third picture here, far on the left. So, Albert talked about you have the head of the fire, you have the back of the fire, and everything in between is flank. It's most easily seen on a slope, for example. So the fire might rush up a slope, but then kind of slowly spread sideways. That's flanking fire. So the other thing about spread amongst fuels is that you have different strata of fuels, because now you're talking about a 3D problem. So you've got different types of fires, different names of fire spread for the different types or names of fuels. So ground fire spread is fire spread through the ground fuels, which are like the duff, the peat, the stuff that's underneath the pine needles. And it's going to be probably largely talked about by Guillermo after me. Surface fire spread is the spread that goes through the surface fuels. So think pine needles, the leaves that are down on the ground, grasses, shrubs, small trees, things like that. Torching fire occurs when you have just maybe one tree canopy isolated, burns, and that's called passive crown fire. But crown fire spread then is where it spreads from canopy to canopy. This is active crown fire spread. There is another thing called independent crown fire spread. It's very rare, but there are stories of the northern lake states where you snow on the ground, but then a canopy fire or crown fire races through the canopy of the tree with snow on the ground. So it's completely independent of the surface fire underneath it. It's really pretty uncommon. So much like continuous fuels, the context of the fuel and those orientation dictates what the dominant heat transfer mode is. So for backing fire, like our opposed flow flame spread, so if you've got discrete fuels, backing fire kind of really depends a lot on fuel continuity. So it spreads along individual particles, much like on a continuous surface. And so fighting a backing fire is relatively easy. All you just do is disrupt the fuel, right? You create your fire break, you dig a line, and that's largely enough to contain the fires and stop the spread. But heading fire, you've got that concurrent flame spread, you've got your flames tilted over your fuel, and whether or not it's convection or radiation actually depends on the fuel structure, which I think Arnaud kind of alluded to, because in wildland fire, the fuel is a very different thing. We're not talking about big surfaces of wood, desks. We're talking a lot about fine fuels. These are the things that carry the flaming front of the fire. They're typically on the order of about 1 millimeter. They're often, especially if you're talking about crown fuels, they're discrete particles dangling in the air, separated by gaps of air, and they're live vegetation, right? So our fuel is totally different. And so I've got a video here to kind of demonstrate why the fuel context matters. So this is a side-by-side of two different wads. This is called Excelsior. So this is just a shredded wood. On the left is a really tightly bunched one, and on the right is a loosely bunched one. And so sitting in front of a radiant heater at like maybe 35 kilowatts per meter squared, something like that. But just watch what happens. So that densely packed fuel, same fuel that's on the right, ignited and burned, and the loosely packed stuff is still just sitting there, not even getting a suntan, right? Oops, I don't need to play that again. To illustrate this even further, I have a video. This is the International Crown Fire Modeling Experiment. Oh, we have sound. So what I want you to do, pay attention to this log, these trees. Got some swap fires, embers falling. Yeah, this log, sorry, this log hit one a lot. So it's pyrolyzing, it ignites, those trees are still standing there untouched. Until that. So whether or not a fuel responds to radiation depends on its size, which, as engineers, we should know this, right? But it's really easy to kind of lose sight that larger surfaces are more receptive to radiation because they don't naturally cool from convection nearly as easily as something that's fine. So this is really illustrated very clearly by looking at the graph here where you have the convective heat transfer coefficient as a function of cylinder diameter. So for things that are larger than about 10 millimeters, natural convection doesn't change much, right? I mean, whether or not you're a log or a big table or a wall, you're only cooling at a pretty minimal rate. But once you get a cylinder that's less than even 5 millimeters, any change in diameter is going to drastically change how quickly you heat up and cool down by convection, right? So that fine fuel is really receptive to convective heating and cooling. And this has really kind of been recently appreciated and realized. So that's a lot of the work that our group has been doing, is to try to understand how convection works in flame spread in a wildland fire. So it is largely kind of ignored for a variety of reasons, I think, or discounted, right? Because a lot of what we know about fire is from fire protection engineering, where we're talking about big wood surfaces. And when we stand next to a campfire or whatever, we feel the radiant heat. So, and it's really easy to just picture a fire as this big wall of flame that's coming at you that's very buoyant. So it doesn't really make sense that convective heat transfer can be happening forward and down into a fuel bed. So we did a bunch of experiments to kind of explore this, and we did it by using a very uniform fuel bed. So historically, we've always used pine needles or big beds of this Excelsior, but it was really hard to see what was going on because no matter how hard you try, there's going to be clumps of fuel or whatever. So we made as uniform of a fuel bed as possible that was repeatable and controllable and able to do it. So we use these cardboard combs. So they have a spine that we stuck into some cement board and the tines stick up. We cut them using a laser cutter so we can really design whatever kind of fuel bed we wanted. We did 62 fires in the wind tunnel with a variety of different tines, lengths, and densities, and how densely packed we packed them with different wind speeds. We also did them on a slope where we looked at different slope angles. And this is what we saw. So I'm going to play this video. And so here we're looking at one of the experiments in the wind tunnel that's spreading toward us. And what's something that you immediately notice? That there's peaks and troughs, right? Like it's not a wall of flame. It's not like a sheet. And if you were to give a kindergartner a crayon and ask them to draw fire, right, they'd probably draw it like that, right? So those peaks and troughs, turns out, are really important to that convective heat transfer piece. And the structure of the fuel and the wind speed and all that changes the frequency of those peaks, but they're always there, right? So once we saw these in the lab and got rid of all of the inhomogeneities and we're like, oh, this is a thing, we started seeing them everywhere, right? So these are grass fires or crop stubble fires and very repeatable peaks and troughs. This is a really large crib fire we did and behind the lab one winter. It was cold, so everybody was getting really close to it. But you also see them in crown fires. So if you look here, it's peaks and troughs. And this was, even written in a paper by Clark in 1999 about seeing peaks and troughs. And what happens is It's actually a fluid dynamic instability. There's a couple of them actually acting here. So if you've got flow over a heated boundary layer, you get these streamwise vortex pairs. And so when they come together and downward, it pushes the flame down into the fuel bed. And when they come together in the upward direction, you get these peaks. And it's really easy to get lost in the peaks because they're the flashy things, but all of the action and the heating is happening in the troughs where it's being pushed down. The other thing that's happening is you have essentially the same mechanism that causes a pool fire to puff. Is you get a puffing mechanism that also helps it move forward as well. So we've got a video here with some flow tracing, and watch the trough with this flow tracing. So you can see really how much heating can happen by convection because of these flame structures. All right. So that's great and dandy, but what happens to the actual fuels, right? So this is some work that Jack Cohen did looking at, he very patiently instrumented a fuel particle in one of these spreading fires. So the red line here is the heat flux that's measured from a radiometer. The black line is the temperature of a 1 millimeter particle that he put out in front of one of these flaming, spreading fires. And the blue line is the air temperature immediately next to that particle. So as the fire approaches, you can see that the radiant heat gradually increases at some point. But we're only looking at, 10 kilowatts per meter squared in the last couple of seconds. But if you look at the blue lines, you start seeing that you start getting some flame pulses ahead. And if you zoom in on the last 20 seconds here, you can see that the radiant heat's still increasing, but even around here, you're only looking at a particle temperature of 100 degrees, so it's barely like drying out at that point. But you start getting these flame pulses indicated by the pulses in the blue temperature, and you see really clearly that the fuel particle then stair steps its way up after every pulse of hot gas. So really kind of drove home the point that you're only for a fine fuel particle, you're really only getting a small temperature rise due to radiation, but there's a lot of cooling from convection. The annotation. And radiant heat fluxes, far ahead are pretty low, right? We talked about radiant heat flux, decreasing as the square distance, right? So it drops pretty quickly, and we see our particles really being stair stepped up to that flame ignition point by that intermediate flame contact. So I'm going to skip spotting and firebrands. We've got to talk on it. Very brief introduction to fire modeling. We've got more talks on this, and it can be an entire semester in itself. I only have about 5 minutes now, so I'm going to briefly go through it. But as we'll hear, there's really 3 main classes of fire modeling, because putting these heat transfer questions back in is really challenging because the context really matters, right? Because if you've got clumpy fuel versus spread fuel, the heat transfer changes. So 3 main classes of modeling: empirical, semi-empirical, and physics-based. And this really boils down to whether it's operational fire modeling or research fire modeling. Operationally, because we need answers really quick, and a lot of the people who are running these models, aren't PhDs in engineering. They run a lot of empirical or semi-empirical models, and researchers tend to use the physical-based models, but for very specific questions, and you can learn a lot of them. Don't get me wrong. But they're not being used by fire managers when they have to decide where to put the dozer line, for example. Not yet. So there's a lot of lectures on these, but so just a brief background. This has a lot of words, I'm sorry. Current operational fire spread models, there's more out there, but there's 3 kind of main ways of approaching it. The way the US does it, we have a bunch of tools and everything that all come down to the same suite of fire spread models under the hood. I'll very briefly go over them. Both the Canadian and Australian systems do their own thing, and they're largely empirical, that are based on fire behavior that they've measured in their own ecosystems, and they have their way of approaching it. I'm not going to go into detail there. But the Rothermel spread equation is at the heart of all of the US models, and in many other countries as well take the same approach. So the Rothermel spread equation is semi-empirical because it starts with an energy balance, but then uses experiments to fill in the blanks. So it doesn't actually answer those questions about how heat is transferred or any of the mechanisms. It's all done with experimental coefficients. And those experiments were done in Missoula Fire Sciences Lab where I work using a few fuel beds of Excelsior, quarter-inch wood cribs, and half-inch wood cribs. But they're all 3 feet wide because that's about what would fit in the wind tunnel, and varying lengths long. So the Raw-thermal spread equation, one of the way it was developed, and one of its limitations is that it assumes a fire is spreading at a steady state and only in the head fire direction. And it was originally developed, as you can see, for homogeneous fuel beds. So they didn't mix and match their fuels, they just did Excelsior or they did wood cribs. It wasn't until we came along later and made our fuel models that we were able to apply it to, a wildland fire. So to do that, there was a correction by Albini to use heterogeneous fuels. So if you've got little sticks and bigger sticks, and how is that all weighted? And it's basically just a weighting scheme for the fuel loading that generated the fuel models. So originally there were 13 fuel models. So if you're going to use one of the models based on the Raw-thermal spread equation, you would say, oh, I have grass. No, I need to go shopping for a fuel model. And you go and you look and you say, well, my grass is so tall, so it's going to be fuel model 2. Or I have timber, so I'm going to use whatever timber model that fits best. Later, we have another 40 fuel models that were added because people wanted a little more flexibility. But it's important to note that we don't have a buoy fuel model, nor should we, because of the way that it was developed, right? So all the models that use Raw-thermal under the hood stop at the edge of a community, right? We can't predict fire spread into the WUI using anything that's based on Raw-thermal. The Raw-thermal, I said, it's basically an energy balance. There's terms here, but we have something called the reaction intensity, which includes things like the net fuel load, the heat content, something he invented called the potential reaction velocity. But you'll note the word empirical here. There's a lot of empirical terms in here to correct for things. So it has an energy balance basis, but there's a lot of terms that he had to fiddle to put in the missing physics, essentially. So that's surface fire spread. For torching and the transition to crown fire, we use a model from Van Wagner from 1977. This is also kind of a similar sort of semi-empirical thing where he comes up with some sort of governing parameters, things that he thinks that should be important, and then fits it to 8 experimental fires, experimental and wildland fires, to get the constants. So for torching, he surmised that it would occur if there's a critical surface intensity. And that depends on how far up above the ground the crown base height starts, so where the tree branches start, and how much energy it requires to ignite those, so what their moisture content is, things like that. And it assumes that transition is actually independent of the crown pulp density. So this is how we predict passive crown fires. So when will a tree torch, essentially? But at the heart of it, again, is a empirical constant based on 8 fires. This is good. For actively spreading crown fires, where we get that transition, when that occurs, he assumes that a minimum amount of fuel has to be consumed to generate enough heat flux to the fuels. So here he has a minimum critical spread rate, which is also empirical. But this is how we predict when a fire is going to become an active crown fire. But once we have an active crown fire, we actually use a different model under the hood to actually predict its rate of spread. And this is actually another one from Rothemel in 1991, but this one's purely empirical. It's based on 8 data points from 7 fires. And specifically, it only considers wind-driven crown fires. We have kind of thrown this concept around a little bit already, but wind-driven fire is where essentially you could look at it and the plume is very tilted over by the wind. Because the ones that were very clearly plume dominated, where you got these big tall plumes, didn't really fit the correlation. And so he just simply related it back to a surface fire rate of spread by multiplying by 3 and calling it a day. So it's important, though, that the key part of this is that the models that we use as a base for all of our management tools are pretty limited in the way that they were developed, right? If they're empirically derived, they're empirically derived on pretty limited data in certain circumstances, and we've kind of ignored others. Or if they were kind of more physically thought about in terms of an energy balance, there's still a lot of empirical things in there. So there's a lot of limitations. And I think Mark and Jason are going to talk a lot about this. But there's a lot of things our fire models can't do because of the way they were developed. To Albert's point, we know the physics, but we don't know how to put all the physics together in a way that we can use it quickly and efficiently to model a fire in an operational sense. So I've listed just a few limitations here. I'm going to save the rest of it for Mark. I think I'll stop here because I know he's going to talk a lot more about this, and I want to save time for questions. So.
All right, so we have time for questions. Yes.
Thank you very much for your presentation. I have a question concerning the experiments that you showed in the Excelsior packages, the loosely one and the other one. And as I understand, radiation heat flux induces a convection cooling, which is, at least for small particles, size dependent. Is this something that we can calculate a priori and know? Okay.
Yeah, I mean, all of our regular engineering correlations for convective heat transfer would work. I mean, challenging because we don't necessarily have great correlations for fuel arrays of pine needles or something, but I think that would be an easy enough thing we can approximate with arrays of tubes or something, but that's a totally achievable engineering thing, is to have convective heat transfer correlations.
And one more question, please. Concerning the peak and troughs that you have observed, is this only observable in the case of a wind or a slope, or is this something that we can observe in a no wind, no slope spread fire?
So that's a very good question. So they are a result of buoyancy. So you won't see them in space. So I think you will even see them in a no wind, no slope fire, just because there's always a little bit of buoyancy induced flow that will create that same instability. They may not be as regular, and because everything's a little more unstable, I guess. I think that's not a great engineering word, but yes.
Okay. Thank you very much.
Yeah, you're welcome.
So the video from the high-speed camera that you showed of the ignition, is it because there was a series of heat input provided by the ignition wire? So is it because of the cyclic nature of the electricity, or?
So the power to the coil was kept constant. So you'll see the same thing if you heat a liquid fuel up. I think I had it on the slide. I didn't talk about it, but it's a common phenomenon with liquid fuels too. So for gasoline versus diesel fuel, for example, gasoline has a higher flash point than diesel fuel. It's one way of quantifying a flammability, and they measure that using an apparatus called a Cleveland cup. So they'll put a little liquid fuel in there, and they'll pass a little flame over it, and you can see the same thing happen even with a liquid fuel, because the ignition process is the same whether it's over a pool of liquid or a solid surface, where you get that premix flame and the heat losses back to the surface.
So the heat input is still constant?
Yes, everything is constant. Yeah.
Thank you. Building on the question of Accenture, sponge, so it's, I don't know, more exposed to the radiation as compared to like if it's open. And the video that you showed there, log which was horizontal that burned, but the vertical tree did not burn. Like it was somehow being like shaded from radiation because of the.
So yeah, I mean that is a very real point. I probably would argue the opposite with the wad versus the loose, because in the wad, you're being sheltered from radiation from the Excelsior on the other side of it. So the whole back side of the wad of Excelsior probably isn't seeing any radiation. So same thing in a forest, right? If you've got a tree right in front of you, it's absorbing all of the radiation and none of it's getting to you. So view factor is another really important thing. I mean, we talk about just even in the open that radiation like drops off really quickly. But if you've got something standing in front of you, you're obviously not going to get any radiation either. So, I mean, yeah, you're not going to get a whole lot of preheating really far away from the flame from radiation at all.
On your experiments with live fuels over convective flow, did you find any sort of property, for example, the genus or the cellulose levels, that differentiates when fuels might ignite through explosions or not? Like, would the essential oil levels in it make any difference?
So that is a very good question, because we don't have a good answer to that. Because not all live fuel species burn as crown fire, right? So I showed examples of ones that do, but for example, an aspen tree leaf won't ignite in a crown fire either. And it has, similar things about hemicellulose, cellulose, lignin, but they're all in different proportions because it's a deciduous tree. It has less lignin, but it also doesn't grow in a place where water is scarce. So it also doesn't have the same structure where it really puts on a hard, waxy layer on the outside. So we can't really tease out the chemical effects of the fuel from the structural effects of the fuel. Like green grass doesn't burn, but a pine needle will. Same moisture content. Like, why? So, yeah, as I say, chemistry, the chemical difference between different species and different seasons is definitely at play. So there's structural things, too, that are different between different species of fuels. And you notice when I mentioned the leaves that had just flushed out that had a really high moisture content but really ignited quickly, that's because they hadn't hardened yet, right? So when a tree puts out new leaves or new needles, they're very soft and mushy and flexy. And they haven't put that hard waxy layer on just yet to protect them from moisture loss. So they have a different structure than the older leaves and the needles. So all of that's at play. So it's a really challenging problem.
Question.
Oh, okay.
Thank you very much for the talk. You mentioned the streamwise vortex pairs, and you said they're affected by buoyancy. Is this unique to discrete fuels, or have you seen any analogy which works in injecting cross-flow or something more canonical in engineering applications?
That's a good question, because I don't know. I think the scale kind of is at play. So when we're talking about wildland fires, the front of the fire is a line fire. So you have a width of flame where you can get away from edge effects, right? So a lot of the more classic things where you're talking about solid fuels in a wind, especially if you don't have any like sidewalls or anything, you get a ton of edge effect, so you can get airflow that comes around. This is really important for larger line fires where the air has to go through it instead of around it. So, yeah, I think it depends on that scale and the size and whether or not, say, you've got that edge effect or not. Does that make sense?
Yeah, one thing to consider one other example. So I think it's just a phenomenon with flow that has curvature. So if you've ever looked at ducts, that curve, flow in ducts, that curve get these counter-rotating tendencies and things too. So it's like a centrifugal force pressure, in the curvature sort of direction phenomena that's causing that.
Yeah.
It's pretty interesting.
I don't think you need a discrete fuel. The discrete fuel is important in the spread, as Sarah explained. But in terms of the flame, the fact that you have continuous fuel source or discontinuous fuel source doesn't matter much.
Yeah, we see it in our, like a pool fire, like a rectangular shaped pool fire with a crossbow, you can get those vortices.
Yeah.
And it's, and you can get it in situations without buoyancy too, like I said. So I think it's a flow curvature thing, more than even buoyancy. Buoyancy happens to be causing it in this case. The curvature of the flow as it hits the flame and curves up. But it's pretty interesting fluid dynamics.
Yeah, it's fluid, yeah,
And
for sure.
What size the vortices break up into, that just, that
Yeah.
change.
Yeah. Yeah. So I guess it's clear that it's not.
More questions up there?
Yeah, go for it.
I wanted to ask, in terms of sort of the geometry of peaks and troughs, in a fully developed wildfire, sort of what's the average distance from trough to trough, and sort of what's that dependent on?
I'm gonna rely on one of these guys to answer that.
Well, it's a good question. Our data, all the data we've seen, suggests that the wavelength, transverse wavelength, is scales with the flame height. Flame length. So that's kind of consistent with the depth of the boundary layer right there. And so there's a variety of studies in fluid dynamics and boundary layer instability that kind of show the same thing, that the depth of the boundary layer is related to the structure in the.
Yeah, I don't remember the proportionality constants to say that a 30-meter flame would have troughs that
About half. About
half. Okay.
But we've never really looked at it across the full range of scales. So we're extrapolating from experiments at relatively small scales.
Working on it. We have stuff planned.
There are some interesting, the boundary layer matters, because remember, we first looked at some things where we have like a rectangular pool fire or a wick kind of fire with no ground in front of it.
Yeah. No leading edge.
And you didn't generate the Gertler vortices is what they're normally called. And so the depth of the boundary layer, even before the fire, seems to matter.
Matters a lot. Yeah, so I mean, like if, in another case, we have a sloping surface where we have fuel on it, basically those cardboard fuel tines that Sarah showed, and without an approach surface before that, and the fire wouldn't spread. We would light it and it would stop, it wouldn't spread. All you had to do is put a preceding inert plane in front of it to allow the boundary layer to develop, and then it spread like crazy. So it's something that, as Jason's mentioning, I mean, the boundary layer approaching the structure of it, and the distance of it, approaching the fire is exceedingly important.
First, we had a question.
Yeah, I had a question on the usage of like the models, the empirical models.
And you say they're sort of obviously quite old, like maybe like 30 to 50 years old, and based on limited data, as you say. Is there any interest in the community on like pooling, I guess, the years of data since that data exists, and then like sort of refitting the empirical equations to more recent data?
So I would say first that the data doesn't exist because politics after, at least in the US especially, once Rothermel had his equation, the Forest Service was like, thank you, and they went and made all sorts of models and training, and basically Dick Rothermel couldn't, continue his research. He then got transitioned to applications of the model. It wasn't really until Mark got started maybe close to 15 years ago doing a lot more experiments. The trick or the challenge, and I didn't have a chance to really get into it, was our models right now, like the number of limitations that they have right now almost makes it not worth going back and tweaking them. So we're actually working on like an entirely different model so that we're kind of fixing some of these things so it doesn't rely on a steady spread and homogeneous fuels. We're trying to fix all of these things that aren't there and put a lot more physics back into it. But we've got better computers, and we've got 15 years of experiments now that we are relying on to put these pieces back in.
All right. Sorry, so last quick question.
I'll be around.
Yes, talking about the theories, do you understand the effect of turbulence on the wildfire spread?
Effect of what? I'm sorry.
Turbulence.
Oh, turbulence. So, I mean, yes and no. I mean, I would argue that this isn't a classic turbulence issue, right? These peaks and troughs, these vortices, they aren't random and chaotic. They are really like repeatable and predictable and correlatable. But yeah, I mean, like, you really want to get into a DNS type model of wildland fire. No, that's where I am. Speaking as an experimentalist.
So have you ever seen laminar flow in a wildfire?
Well, yeah, the flames are small enough.
Like, in a wildfire?
Yeah.
Well, let's thank Sarah again.